Greetings and welcome back to our lecture series for Calculus 1. It's packet 2017 on section 4.4, concavity. So this one's talking about the second derivative and concavity, and there are two major outcomes from this section. The first one is to understand that the concavity of a function is determined by the SIGN sign of its second derivative, f double prime. The second one is that the second derivative attempts to classify critical points as local minima or maxima based on the sign of the second derivative at the critical point, that is to say, the concavity. So we're going to try to use concavity to determine whether critical points are local mins and local maxes. I do have two YouTube videos about this that I would link as well, in case you like the Lightboard format more than this format, although this format is more comprehensive. So the first thing we need to do is we need to talk about concavity. What is concavity when we say concave? Concave up, concave down. What do we mean? Well, it's all about describing the way that f prime, the first derivative, changes. For example, if the function is increasing, is it increasing at an increasing rate or at a decreasing rate? This is particularly relevant to us right now in the face of COVID. If the infection rate is increasing, then there are more infections day on day. And if it's increasing at an increasing rate, then tomorrow, not only will there be more infections, but the infection rate itself is going to go up as well. So this I think is particularly relevant in the pandemic that we're living through right now. So let's focus on the definition, the formal thing, and then we'll do two pictures to illustrate what I mean by this. So focusing on the definition, let f be a differentiable function, fine. The reason that I need that is because we're going to be talking about f prime, so we have to be talking about something that's differentiable. On an open interval, then we're going to say that f is, quote, concave up on this interval if f prime is increasing over that interval. And similarly, it's concave down if f prime is decreasing on that interval. So I'm going to draw two pictures. On the left-hand side, I'm going to draw a function which is increasing, and a function which is f is increasing and f is decreasing. And so generally that means that my function is going to be going like up or down. But now we're talking about the way it's going, the way that f is increasing is itself increasing. So let me delete both of those lines. So if f is increasing, then it must be, as we move to the right, it must be going vertically up. That's what it means for it to be increasing. And it's doing so at an increasing rate. So it's getting more vertical toward infinity. And then if we let that keep going like that for a while, and then let's let it do this. So here f is still increasing, but it's getting less steep. Similarly, let's turn to the right one. Let's draw a decreasing function. So if I'm drawing a decreasing function over, as we move to the right, it's going down. I don't know. I always puzzle about like which color should I use to do this. So f is going down, right? Because it's decreasing. Let's make it be getting steeper and steeper. Then it's decreasing at a decreasing rate. And that is to say that f prime is moving towards minus infinity. And then let's let it kind of like level off like that. So right over this interval here, f is decreasing, but at increasing rate. That is to say that f prime is moving towards positive infinity. Let's see here. Yeah, so this is f prime is moving toward negative infinity. Okay, so I want to do one additional thing, and I'm going to draw the concavity arrow. So I'm going to put a dot. See where I put that dot? Put that dot right there. I put that dot because that splits where I get to draw a down arrow and an up arrow. Over here, it's concave down. Over here, it's concave up. Let's do the same thing with this diagram over here. Let's label as concavity. Let's put a dot at the place where it changes. And then let's draw an arrow down. And then let's draw an arrow up. It's concave down and concave up. So regardless of whether f itself is increasing or decreasing, it can still be concave up or concave down. So in a sense, there are two properties of f that we're interested in, right? Is f increasing or decreasing, and is it concave up or concave down? And it can be either one of those two things for each of those two categories. So there are 4 possible combinations. And this is going to be particularly relevant looking forward to section 4.6. Let's turn the page. All right, cool. So that's all fine and dandy. But really, like, what's the computational tool that we're going to use to understand concavity is the second derivative. Because if the first derivative has to be increasing for it to be concave up, then the second derivative is positive, and that's exactly what's said here. If f double prime is positive, then f is concave up on A, B. And likewise, if f double prime is negative, then f is concave down on that interval. One piece of information that I want you to take note of here is that this can only change, right? F can only go from, f double prime can only go from positive to negative or negative to positive across places where f double prime either equals 0 or f double prime does not exist. And so these are not what we call critical points. These are what we call possible inflection points. And I've got more content on that down below. So, yeah, so I guess I need to define an inflection point. And then the theorem down below is going to tell you how to computationally do it. Okay, so let me give you a quick little definition. A point C is an inflection point of f if f changes concavity at C. So, for example, if I go like that, then this right here, that's an inflection point. Because it went from concave down to concave up. In contrast, if I were to draw, nope, I wanted red. If I were to draw that, perhaps, this has concavity down the whole time. And so even though right here, that's a critical point, there's no inflection point there because it's concave down over that entire interval, right? So I think that understanding this in terms of drawing the arrows up or down, to me, is the most powerful way to deal with this. So I've got a theorem here, and that's that if two things happen, if f double prime equals 0 or f double prime does not exist, and in fact f double prime changes sign, then f has an inflection point. I think 2 implies 1, but 1 does not imply 2, because just because we have one of these two things right here, we call that a possible inflection point. Let me go ahead and make that permanent here. Number 1 right here says that C is a possible inflection point. And then 2 is the thing that says, no, it really is an inflection point. Okay. So let's do some examples, and then we'll talk about the second derivative test for classifying points in domains, critical points, as optima. So let's find the inflection points of cosine from 0 to 2 pi. If I did it without respect to an interval, then it would have an infinite number of inflection points. And so we're going to restrict ourselves to an interval of interest. So let's restrict ourselves from 0 to 2 pi. Okay, cool. So we're supposed to find the possible inflection points, find the inflection points actually. So let's, we have f equals cosine of x, then we have to pass through single prime first. I can't go directly to double prime. Okay, maybe you can. Maybe you know that f double prime is minus cosine of x, because taking two derivatives of one of the basic trig functions, sine or cosine, gives you a minus sign. But whatever. So f prime is minus sine x, and f double prime is equal to minus cosine of x. So the possible inflection points are where f double prime equals 0, and that means that 0 equals minus cosine of x. That means that 0 equals cosine of x. Drawing cosine, I know that it goes like this, from 0 to 2 pi. I happen to know that that's pi, which means that we have two places, pi over 2 and 3 pi over 2. Okay, these are the two places that we can have possible inflection points. So we have possible inflection points at pi over 2 and 3 pi over 2. And now we need to check, does f double prime change sign? And in this particular case, I want to use a graph to do that for me. And I think I'll use this graph. At pi over 2, this is a plot of f. Oh, I need to flip it upside down. I can do that. Oh, I wanted that in red though, didn't I? Let's make it pop. Okay, so that is a drawing of minus cosine of x. That's f double prime. And in the region to the left of pi over 2, this is where f double prime is negative. So we can conclude then that on this interval right here, f is concave down. And then in this interval right here, because f double prime is positive, that means that the original function is going to be concave up. And we're saying f is a concave up because this right here is a picture of f double prime. And then similarly, here is where f is concave down. So let's draw on this picture over here a picture of the cosine function. Let's say cosine starts at 1. We're going to go like there's cosine. That is cosine of x. Now let's draw the concavity arrows. Down, up, and down. Let's see that we have correspondence in the other thing that we labeled over there. So concave down. Here the second derivative is below the x-axis, and we labeled that f as concave down. From here to here, from pi over 2 to 3 pi over 2, we can see with the concavity arrow that f is concave up, and indeed we noted f is concave up. Similarly for the last interval, we are not quite done. We need to conclude with this. We have these possible inflection points, and so I think we'll finally conclude and say at the very bottom here that yes, f double prime does change sign. So both pi over 2 and 3 pi over 2 are, in fact, inflection points. Let's move to the next page. Let's play with the inflection points of another function, shall we? Let's find the inflection points of x to the 5/3. Possible inflection points are given where f double prime is 0 or undefined, so we need to pass through f prime. So using the power rule, and then again, all right. So that's our derivative, just two applications of the power rule. Now we're going to ask where is f double prime 0 or undefined? The answer is that it's never 0 because looking at the function, the 10/9 doesn't matter whatsoever, so you can ignore it. Then we have this thing right here. The only way for that to be 0 is if the numerator was 0, but the numerator is a constant 1. And so this part right here is never 0. So f double prime is never 0, but it is undefined. It's undefined at x equals 0, right? Because that's where in this expression, if you put in a 0 right here, then you would have 1 over 0, which would be like, infinity. So undefined. Undefined is 0. All right. So we have in one possible inflection point. 0. Is it an inflection point? Does the concavity change across? Well, let's do that by labeling right here x equals 0 on our axes. And I know that that is, in fact, the only place the concavity could change. It can't change anywhere else, which means I can do what I did for the first derivative test and say take some test point over there, and all I have to do to label as down or up, to get those, I'm going to evaluate at the test points. And what am I going to evaluate? I'm going to evaluate f double prime at those test points because that determines the concavity. So I know a convenient point just to the left of x equals 0. Let's call that -1. let's call the other one 1. So the test point of -1, I need to know f double prime of -1. That's equal to 10/9 times 1 over -1 to the 1/3, which is less than 0, which means that I have a concave down function there. And then if I go to the right, let's take our test point as equal to +1. F double of +1 is equal to 10/9, 1 over 1/3. That's bigger than 0, which means that over to the right over here, I can erase that. And I know that my function is concave up just by evaluating f double prime at that test point. No need to plot, just use a convenient point to do that for you. All right, so to wrap up, I have this possible inflection point x equals 0, and we just determined that it does in fact change concavity. So f changes concavity across 0. Therefore, x equals 0 is an inflection point. All right, so now hopefully you know some about inflection points, possible inflection points, concavity, all those things wrapped up in the second derivative, which means we're ready to talk about the second derivative test. That is to say, the second derivative test for classifying critical points as being local mins or local maxes. So when I say the second derivative test, I mean the second derivative test for classifying. Classifying critical points. So I want to make an observation for you on these two axes that I have right here. First thing I'm going to do is draw a picture of a max. If I have a max, it's going to look something like that. So I'd have some thing C. We've got a critical point there, and let's draw the concavity. This is concave down. And all maxes look like that. Similarly, if I have a min, so I've got a minimum right there at some critical point C. It's a critical point. Then this works for undefined critical points as well. Where f prime is undefined, except that's a damn lie, because if f prime is undefined, then f double prime is most certainly undefined. So this only works for critical points where the derivative is 0. It's going to fail otherwise, because f double prime won't be defined. Anyways, if we draw a concavity arrow, it's concave up, and we've got a min. Okay, so min at C of the local flavor corresponds with f double prime is bigger than 0 because it's concave up. And a local max at C corresponds with f double prime at C is less than 0. Or concave down at C. And that's essentially the second derivative test in a nutshell. If you understand these two diagrams, then I think that you're going to be down with the second derivative test. All right, so this theorem essentially is the second derivative test, but not in a sequence of steps to do. I have that written in a flow chart. So a theorem says, if I have a critical point, and if f double prime exists, then if f double prime is less than 0, we've got a concave, or we've got a local max. If f double prime is greater than 0, then it's concave up. And I've got a local min. If f double prime of C equals 0, and the alternative is, or f double prime does not exist, then I've got an inconclusive test and we should use a different test. That is to say, we should probably turn to the first derivative test for classification. There are pros and cons of using each of them. Okay, so I made a flow chart. Hopefully you found these good. The first thing that we're going to do when we do this is we're going to examine the givens. Like, how do we know that we're going to want to do this? Well, I'm going to be given a function, an interval, maybe. Maybe you're not given an interval. And instructions that we want to find, classify, analyze, local optimum over F. If they tell you to use the second derivative test, do it, right? And if they don't specify, then which test to use is up to you. Because you could also use the first derivative test. So first thing that we're going to do when we're actually doing this, I like constructing a table. And this is going to be a table of x's and classifications. So I'm going to have x, and then we'll have its classification. I'm going to add my endpoints, A and B, if given. And then after that, I'm going to add my critical points. And then I seek to make a classification, and what I want to put in here is like min, max, or it might be an I don't know. Right? We're going to have that for each of these. So we will have a min, a max, or an I don't know. And these are all with the local modifier. I'm just omitting the word local because it is a lot. All right. So you already know how to find critical points. Because we've already done that several times now. You're going to take the derivative of f. You're going to solve where it's undefined. You're going to solve where f prime is equal to 0. And you're going to take those things and put them in here because those are your critical points. And we're going to classify the critical points as being mins or maxes. Okay, so that sets us up for that. And now we need to get our classification tool online. And that classification tool for me is a number line. I really like using the number line. So the first thing that we're going to do when we do the number line, so I'm going to be like, boop, there's my real numbers, and I'm going to label those as x's. And what I'm going to add to it are possible inflection points, right? So possible inflection points, and then concavity information. Right? So how about I call the possible inflection points, these collection right here are my piece of i's for my possibles. Right? I'm going to put those on here, and we'll just put as many as I have. So that's going to help me with my number line. And now I need to determine the sign of the second derivative. Oh, I think that should be inside the create number line box. All right, so now we're going to do that. Now we're going to do that test point thing. So for each interval that I have inside of that thing, for each interval I have inside of that thing, I'm going to choose a test point. Right? Right? The values of those are up to you. Choose nice numbers, right? Any number that you want inside of there, choose it. And then we're going to evaluate the second derivative, and we're going to write the plus or the minus, or I like to use arrows to indicate the concavity. And so, so I'm going to be like, okay, it was concave up. Okay, cool. In this interval, it was concave down. Wow, those are like, highlighter is not useful in this context. But I do like bright blue, right? So we'll label with like concave down, concave up, concave up, concave down. Say that's the signature we get. Cool. So I probably, I don't know, like I usually, I may or may not actually add my test points to this because now my number line is a bit like, I feel like my number line is a bit cluttered. And what I really want is kind of like this with my P1, my P2, my P3, and just like down, up, up, down. Like kind of that's all I want because this is my classification tool. Because the next thing we're going to do is we're going to be like, well, what's the concavity of the critical points? And so for each critical point and boundary point as well, we're going to go grab, right? We're going to go grab these from the table. I've got these in my table. And so now I want to figure out for each of my C's, right? Here's like C1, here's like C2, here's C3. I want to see which interval does the critical point fall in, and I'm going to grab the up or down arrow from that interval. So sometimes I find it nice to go ahead and add the like the critical points to this. So here I might be like, well, that's where C1 is. Okay, C2, C3, C4. So I might do something like that. And then you just have to figure out, oh, okay, for these two critical points, they were inside the up arrow right here. And so that's the classification. We know that C2 and C3 are in an interval where the function is concave up. And that means that I've got concave up, up, is like that. Okay, it must be a min. Okay. So we're going to examine the concavity at each of the critical points using the intervals. And then we're going to figure out, is it concave down? Is it concave up? Or is it neither? Which of those three things is it, right? It's going to be 1, 2, 3. And it's really like, we don't know what it is. And so like, if it's concave down, I like, right? Concave down. That means we've got a max. Concave up, we've got a min. Second derivative test inconclusive. That's where f double prime is undefined or 0. Fine. In any case, we're going to conclude by clearly writing our conclusion, referring to what we were given in our problem statement to make sure that we're concluding the correct thing about. Are we answering the question we were asked? Okay. So hopefully you find that flowchart useful. Probably make one for U substitution in a few weeks. Okay, so let's do two examples of the second derivative test. One where we're going to have a conclusive outcome and an inconclusive outcome. Okay, so let's analyze the critical points of this function f is 2x minus x squared times e to the x. Okay, cool. No problem. Our first step is we're going to find the critical points. Okay, that's where f prime equals 0 or undefined. That means I need f prime. And let's go ahead and use the product rule on our function. So we're going to product rule it when we take this derivative. And I'm going to have 2x, nope, erase. Oh, actually, that was correct in a weird manner of speaking. But I was going to be like 2 minus 2x times e to the x plus 2x minus x squared e to the x. Right, and I want to know where that's equal to 0. And I'm not going to write equals 0 there. I'm going to do that on a separate line. 0 equals 2 minus 2x e to the x plus 2x minus x squared e to the x. The first thing I'm going to do is I'm going to pull out an e to the x of both of these so that I have 0 equals 2 minus 2x plus 2x minus x squared. The whole thing is times e to the x. And now I'm going to divide by e to the x. Because it's never 0, I can do that. that's going to cancel, and I'll be left with 0 equals 2 minus 2x plus 2x minus x squared. Cancel, cancel. That is to say, the 0 equals 2 minus x squared, which means that x is equal to positive or negative square root of 2. So I've got myself a table, x's, and conclusions, minus root 2 and root 2. Those are my crit points. All right, so now I want to classify each of those things. And what I'm going to do is I'm going to construct my number line. And I want to put on here, I'm going to put my possible inflection points. So now we're going to need to find those. That's where f double prime is going to be 0 undefined. So let's take f double prime. How about we take an easier version of this? Instead of doing the product rule twice, let's simplify f prime, because I don't really want to do the product rule twice. That's equal to 2 minus 2x plus 2x minus x squared e to the x after factoring out the e to the x. Right, so those both came out and turned in there. Then that's going to cancel, and that's equal to 2 minus x squared e to the x. All right, so let's repeat that. 2 minus x squared e to the x prime. Product rule. Minus 2x e to the x plus 2 minus x squared e to the x. Let's find where it's 0. Noting that f double prime is never undefined. Why is it never undefined? Well, because it's always a finite number, because each of the pieces always generates a finite number. So we want to know where does 0 equals minus 2x e to the x plus 2 minus x squared e to the x. Let's factor out an e to the x again, and then divide by it. So let's cancel those, shall we? 0 equals minus 2x plus 2 minus x squared. All right, 0 equals minus x squared plus 2 minus 2x. I'd rather have it be modic, and so we'll have 0 equals x squared minus plus 2x minus 2. There we go. Sorry, I wrote this in a different order than I expected to. Boop. No, now the signs are wrong. Boop. Boop. Yes, yes. Alrighty, we reduced this to the problem of factoring a quadratic. I've been doing that since 7th grade. I have x minus 2, x plus 1. Ooh, do I? Ooh, I think I'm going to use a quadratic formula for this one. Because that's not a 3 or a 1 in the middle there. Did I do my work correctly? I think I did. I think I did. I'm gonna go back and recheck my work here. I think I might have made a mistake. Not because I know what the answer is, but just because I know myself and I feel like I made a mistake. It's gonna be okay. All right, fine. We'll use the quadratic formula. So x is equal to let's see, quadratic formula, minus 2 plus or minus the square root of 4 minus 4 times 1 times minus 2 all over 2. That is a minus 2 inside of there. Alrighty, so that's x is equal to negative 2 plus or minus square root of 12 over 2. It's 1 plus or minus, negative 1 plus or minus the square root of 12 over 4. And that's just equal to 3. So it's negative 1 plus or minus root 3. Fine. Negative 1 minus root 3. Negative 1 plus root 3. All right, so we have 3 intervals. 1, 2, 3. 3 intervals. Let's label some test points. I know one that I'm going to put in here. 1. I know one that I want to put over negative 1. I know one that I want to put in over here. Let's go that minus 5. That seems good. And then how about over here? Let's go with that being 5. Because why not? So let's evaluate f double prime at each of those test points. F double prime at minus 5. We need f double prime. So if we repeat this calculation, we'll find that f double prime is equal to x squared plus 2x minus 2 times e to the x. Ooh, check this sweet little ditty out. This right here, e to the x, that's always positive. So the SIGN sign of f double prime comes from this. So I'm just going to evaluate that part. Okay. So f double prime f double prime over e to the x is equal to that part right there. And then f double prime over e to the x of minus 5 is equal to 25 plus 10 minus 2. That's bigger than 0. Concave up. F double prime over e to the x of negative 1 is equal to minus 1 squared minus 2 e to the x. Ooh, that's negative. Concave down. Now I kind of don't need those test points anymore, so I'm just going to delete them. And then finally, let's take f double prime over e to the x of positive 5. That's going to be equal to 25 plus, ooh, I made a mistake earlier, 10 minus 2. This minus sign here was supposed to be, this plus here was supposed to be a minus. Did not change the SIGN sign. All right, we found that that second derivative was positive, and so I know that this number line here is the signature of this second derivative. The function goes concave up, concave down, concave up, and it's separated by these 2 inflection points. So all that remains is I need to place minus root 2 and root 2 in context here. Let's remind ourselves that root 2 is about 1.41 and root 3 is about 1.73. So negative 1 minus root 3 is about minus 2.73. Negative 1 plus root 3 is about 0.73. So in order to place root 2 and minus root 2 on this, okay, so minus root 2 is over here. It's about 1.41 with a minus sign in front of it. Okay, so we've got the function is concave down. That means I have concave down, max. And root 2 is over about here maybe, 1.41. Concave up. Nope, that was the wrong way. Concave up. Oop. Concave up is a alrighty. Okay, so that was quite a lot. These problems are admittedly involved, but they're really quite procedural once you get all the way through understanding the process. So let's do one more of these real quick. And then the point of the next one is sometimes the second derivative test is inconclusive, and I really wanted to do one of those. So. Did I make a mistake? I think. I think I might have messed up an SIG and sign somewhere. Oh, you know what? You know what I did? Yeah, okay. I know I found an error. I found a major error in this, and it's a major error in terms of SIG and sign. So I'm missing a minus sign on this right here. And I'll point out where it was. So that's actually a less than and a bigger than. So these arrows are all wrong. So I said it was up, down, up. It's actually down, up, down, which means that the max and min conclusions are flipped. I do apologize about that, but I'm glad that I caught it. All right, so where did that minus sign come from? Again, I forgot a minus sign on that. I accidentally looked too far. I looked at that line when trying to play with finding stuff for the SIG and sign. And there I'd like dealt with this minus sign by like kind of throwing one over to the other side. So it was actually this expression that I wanted right here, and that's off by a minus sign from what I was using. And so to correct for that, I added this minus sign in those places, which flips those, which flips these arrows, which flips these two things right here. I do apologize about that. I cannot go back and undo that in this video. Let's do one more, and then we'll call it good for the day. Let's play with this function, which I call g x to the fifth minus 5x to the fourth. We're going to analyze its critical points. Critical points are where g prime, undefined, or 0, but there are no places where g prime is undefined because it's a polynomial. So we just need g prime, that's 5x to the fourth minus 20x cubed. And that's going to be 0 when we have 5x to the fourth minus 20x cubed, or 0 equals x cubed times 5x minus 20. And let's get rid of those 5s by dividing everything by 5. So I have 0 equals x cubed times x minus 4. All right, so I have two things right here that emits two critical points. At 0 and 0 and plus 4. Zero, 4. All right, so now we just need to see what the concavity of those two things is. No problem. I'll take the second derivative. G double prime equals, I'm looking back to my original line right here. Let's take that derivative. 20x cubed minus 60x squared. That's always defined, so only has 0 possible inflection points. 0 equals 20x cubed minus 60x squared. That's either at, well, let's factor this. Let's divide everything by 20. And then let's factor out some x's and rewrite this as 0 equals x minus 3 times x squared. So I get, as a result of this right here, 2 possible inflection points at x equals 0 and x equals 3. I like doing a number line. If you're not enjoying the number line, I don't have a problem with that. 0, 3. I have 1, 2, 3 intervals. I'm going to choose convenient points in them to determine the concavity. Or really, I mean, if we want to like be a little bit more optimal, what we could do is we could be like, well, I only need the concavity at these 2 points right here. So let's save ourselves from some work, shall we? X equals 0 is a critical point. It's also a possible inflection point. So I'm going to flip back 2 pages, and we found if f double prime is 0, then the test is inconclusive. So what we found is that f double prime is 0 at 3, which means that for x equals 0, the test is inconclusive. However, at x equals 4, we have a critical point, and now I just need to say evaluate the second derivative there. F double prime of 4 is equal to 4 minus 1 times, and no, I should use the actual function. The actual function is this one. Because all I care about is the sign, so I really don't care about scaling it by 20. Whatever. 20 times 4 cubed minus 60 times 4 squared. 20 times 4... 64 minus 60 times 16. Which one of those is bigger? Let's write that as 20 times 64 minus 20 times 48. So I took out a 3 and I put it into here. It's pretty clear that the 64 is bigger than the 48, so this number is going to be positive. So that means that at x equals 4, my function is concave up, and I have a min of the local variety, if you're really into it. I am. We should be unambiguous. Okay, so that's the second derivative test. All you have to do is find critical points and then evaluate the second derivative at them. I hope you find the flowchart on here useful. And I think one of the cool things that we just found in this last example was that there is a possible optimization that you don't actually have to find the concavity for every single one of the intervals. You really only care about the concavity at each of these 2 things. And so you can just evaluate the second derivative there. But I'll stop there and say thank you so much, and we'll see you next time.